In this module, we discuss searches for new phenomena beyond the known ones described by the standard model. In this video, we will discuss searches for tails in characteristic event distributions. This type of searches are, for example, typically used in searches for supersymmetry. After watching this video, you will know how we typically search for supersymmetry in hadron colliders, what is the main challenge of these searches in the busy proton-proton collision environment, and where we stand in our searches for supersymmetry and new physics in general, using the ATLAS experiment as an example. We are typically searching for new physics looking for bumps on a steep falling spectrum or looking for enhanced tails in the distribution of a relevant quantity. We already talked in the previous video about bump searches using the heavy Z boson as an example. While this type of searches is very intuitive and convincing in case of a positive result, such bumps are not easy to identify in the case of supersymmetric particles. Supersymmetric particles decay in cascades, generating long decay chains, which make it difficult to identify a resonant signature. Given the large multiplicity and variety of particles in the final state, we are typically looking for an enhancement in a tail of a distribution. Relevant distributions can be related to the multiplicity of a specific type of object, for example jets, or to missing transverse momentum, which in many variants of supersymmetry is enhanced by the emission of neutralinos. These are the lightest supersymmetric particles, neutral and weakly interacting, escaping the detector just like neutrinos do. In a SUSY search, we are therefore looking for signals that way, where a relevant quantity can be the missing transverse momentum. The standard model backgrounds, given the large number and variety of objects involved in these searches, are very complicated to estimate. For background determination, we are using data-driven methods combined with simulation-based techniques. We use standard model processes with similar characteristics to verify that the detector response to an assumed signal, properly simulated, is indeed as expected. In this type of searches, the usage of multivariate discriminants is not uncommon, and attempts to achieve a more powerful discrimination of the signal with respect to the background. To increase sensitivity in models that involve large multiplicity of B quarks in the final state, like the one shown in this page, we reconstruct jets originating from a B quark. We use the knowledge that hadrons containing B quarks travel a short distance inside the detector before decaying. Stable hadrons, on the contrary, come directly from the proton-proton vertex. We also reconstruct top quarks from their decays using their kinematic properties. The top quark decays to a B quark and a W boson before forming a hadron, and with a branching ratio close to 100%. The W boson decays most often to a quark pair. When the top quark has a large momentum, its decay products are more collimated, as shown in this picture. At high top quark momenta, some of the jets cannot be disentangled from each other. It is therefore common to define wider jets, called fat jets, which capture the products of the decay of a high momentum top quark. We can therefore require, for example, the presence of multiple fat jets in collision events, a requirement that can improve the signal-to-background discrimination compared to an event selection that does not include such requirements. You can see in these figures examples of how final distributions look like. The field areas show the standard model prediction, while the dashed line shows how supersymmetry would manifest itself. The black points show the observed distributions, which agree very well with the standard model prediction. What is shown here were in fact two signal regions with the largest excess on the left and largest deficit on the right of a specific search. The agreement with the standard model predictions is usually even better than what is demonstrated in these examples. Getting tails of a distribution right in Hadron Collider data is a very significant challenge. Many experimental factors can alter the expected distributions, therefore careful study goes to distributions with similar properties but coming from well-known processes. This ensures an excellent understanding of those factors and the associated systematic uncertainties. One of the most significant challenges comes from what we call pileup. At the LHC, protons don't collide individually, but in bunches of hundreds of billions of protons. This results in multiple collisions in a bunch crossing, leading to several low Q-square reactions. Distinguishing the hard scattering process from the rest and understanding how pileup affects the distribution of interest are both very difficult tasks. In the Hadron Colliders, we have achieved a significant level of understanding, having thoroughly studied the LHC data collected so far. Having looked at a very broad spectrum of signatures, we have not yet found any significant excesses that could hint to new physics. In lack of excesses, we put limits to the theories and models that have motivated our searches. That way, we can obtain a global view of where we stand with our searches and ask theorists about their advice on which direction to take in our future searches. The figures in this slide give the current picture for all ATLAS searches for supersymmetry and other new phenomena. They are all expressed as lower limits on the mass scale that characterizes the process. You can see that we are close to excluding supersymmetric particles up to 2 TeV in mass. Despite the fact that supersymmetry and other theories beyond the standard model remain elusive so far, the open questions of the standard model are so pressing that it is certain there is something beyond. With the increasing amount of LHC data that is available, we are on the right track to find what that is. We are faced with a unique chance to make a unique discovery at the LHC, and history had taught us it may be unexpected. At the LHC experiments, we are looking forward to that.